certain point, so it's a negative quantity. So when we study how it varies as we move away from the surface of a planet, we have all the values appearing on the negative side of the curve, with the negative values of gravitational potential energy appearing on this side of the curve, and distance along the positive x direction. So if this is distance and these are the values of gravitational potential energy, the negative quantities, this is the gravitational potential energy as we move away from the surface of a planet. So as the distance is from the center of the planet, but usually the values are measured from the surface of the planet, because the minimum value of gravitational potential energy is taken at the surface of the planet, and the largest is as the infinity. But what happens if instead of one mass, you have two masses placed side by side? Let's say you have a mass here, and at a certain distance away you have another mass here, and there is a separation mentioned between these two. The surfaces have a separation mentioned, and the gravitational potential energy is to be shown varying between this space. Then what change in this curve is expected? The change is something like this. That means the gravitational potential energy or gravitational potential, as I mentioned last time, the two values have a similar trend on the curve. If I take it gravitational potential instead of potential energy, it will become phi. The question that I have selected for discussion gives the values of gravitational potential on this side with negative values given here, and the value of distance as we move from the surface of one mass, which happens to be a planet, to another mass which is of comparable size, and this is approximately the distance to which we have moved. And the question is about what happens to the gravitational potential energy and the kinetic energy if this object is allowed to move freely between the two masses. This curve is given, and you will remember that this curve is always representing the variation of gravitational potential or potential energy of any mass whose values may be given or maybe calculated from the given information if that mass is moved from this to this position. So this is a curve showing the values of the gravitational potential energy. At the surface of this planet, the value is given, and let's say that value is minus 10 into 10 raised to the power 8 joules per kilogram, something like this. This is the value, and when an object is moved a certain distance from it, it moves here, let's say, and at a certain position I want to know what is the value of the gravitational field here, the net field between the two, and what is the net force due to two masses acting on that mass. Suppose I select a position, and the position is something like this, and I want to know what is the value of the net field here. As I discussed last time, if I want to calculate the gravitational field at a point, I draw a tangent to it and then I calculate the gradient. If I know all these values of distance and I know all these values of the potential on this side, and I draw a tangent here, this tangent obviously gives me the gradient, and the gradient will be equal to the net gravitational field, which is the value of G between the two planets. And if I want to calculate what is the force as a result acting on that mass, if suppose using these values and using this rise and run, I get a certain value, let's say 2 into 10 is power minus 3 meter per second square, something like this. And I also have the value of mass that I am moving here, then I know what exactly is the weight, which is the force that this mass is experiencing due to the net value uh, of the gravitational field between the two masses. So if I use F is equal to mg, I can calculate the weight. If 180 is the mass, I multiply it by this value of g, I get the net force acting on that. So important point to remember is whenever you have a curve like this, you can calculate the gravitational field at any point. You can see the gravitational field. If we go on moving to the top, the gravitational field becomes smaller because the slope is becoming smaller. So gravitational field may be decreasing as you move away from this planet, and there is a point where the curve becomes, where the tangent becomes exactly horizontal, and it is expected because there will be a point between two masses where the fields will cancel, as I discussed earlier, that the gravitational fields cancel between two masses at a certain point, and definitely that point will be slightly closer to this smaller mass. So somewhere here we expect that the slope of this curve will be 0. So gradient will be 0 there. So gravitational field will be 0 there. The mass will not be experiencing any force. But this is not the case with the gravitational potential energy. Gravitational potential energy is never 0 at any point. That means you have to do some work in order to bring that mass from infinity to that point, and therefore this curve doesn't touch 0 value. So gravitational potential energy is not 0 at any point between the two masses. But this is the kind of variation we have. The gravitational potential energy initially very small, and it gradually increases and becomes maximum where the gravitational field is 0, and then the gravitational potential energy again decreases, which means it becomes more negative as you move towards the surface of this planet. This simply means that in order to raise an object, you have to move against the field, and then beyond this point, if you leave that object in its own and allow it to move freely, it will fall automatically to it because the gravitational field is on this side, and beyond that point, the object under the influence of the field of this mass, this object will fall freely on its own. But you have to do some work in order to raise from this to this point, up to which the gravitational potential energy is increasing. That means just like you have to do some work to raise an object to a certain height if it is initially on the surface of the earth, similarly you have to put in an effort, you have to apply a force, you have to do work in order to raise it to a certain height. But after that, when you leave it, the object falls on its own. So if they give you values, two values of potential, and then ask you what will be the kinetic energy of the object if it is allowed to move on its own, after that we can also calculate. And let's see if we have these values here in the question, so we can calculate the kinetic energy. Suppose on a similar graph, they give us two values of potential and then ask what is the kinetic energy of the object if it moves between those 2 points. That means if an object is allowed to move, let's say from this point to this point, that means it is falling on its own, its potential changes from this value to this value. So as a result, its potential energy will decrease and therefore its kinetic energy should increase. So let's see how we do it. In this question, they have given us two values of potential. What is the change in potential if initially its value is phi 1? This is if it is minus 1.8 into 10 raised to power 11 joule per kg, and another value is minus 2.52 into 10 raised to power 11 joule per kg. Which one is larger value? This is larger value of the gravitational potential because this is less negative number. So this phi 1 is greater value than this one. That means you are close to the top of the curve and this is at the lower position of the curve. If you take the difference of these two, I mean if you take it as phi 1 or phi initial minus phi final, you get the difference of these two, which comes out to be something like 7.2 into 10 raised to power 10 joule per kg. If I take this as initial and this as final, this minus sign will make this as positive. So these two values, this will become a positive number. So ultimately, this is the result that I have. So change in potential is this. If I know that this is the change in potential and I multiply it by the given mass, which is 180 kilogram given in this question, this can be written equal to half mv square. That means if an object is allowed to fall in the field, it initially has this potential and therefore a certain potential energy, and finally it has this potential and therefore a potential energy. So change in potential energy should be equal to the change in kinetic energy. Obviously the object is falling freely, so there is a decrease in potential energy. A decrease in potential energy must correspond to an increase in kinetic energy, and the basic physics remains intact. You just have to see these values carefully, do this calculation carefully, taking care of the negative signs, and if you calculate the decrease in potential energy, that is actually the corresponding increase in kinetic energy. So this was the last part of the change in gravitational potential energy, which specifically deals with how it varies between two masses. Instead of a single isolated mass like planet Earth or any star, if two masses are considered side by side, it's an Earth Moon system, it's a Sun Earth system. The variation of gravitational potential energy is the curve that I have shown, and with the help of that curve we can do these calculations. One more thing we can add to our today's discussion is the idea of escape speed. Escape speed is the speed with which an object has to be thrown from the surface of a planet, so the object leaves the gravitational field permanently. If we are initially at the surface of the earth and an object is to be thrown with a certain speed, so it reaches infinity, which means it leaves the gravitational field, the minimum speed with which we must throw it from this is known as escape speed. So if I define escape speed, it is the speed required in order to leave a gravitational field. So if you want to throw a ball with a speed so it leaves the gravitational field, which means at least that speed with which it reaches infinity will be the escape speed. Let's derive its formula. We have a certain value of gravitational potential energy here, and we have the gravitational potential energy here, which is 0. This is gravitational potential energy of any object taken at infinity 0, and the gravitational potential energy at the surface of the earth is minus g m over capital R. This is the mass. Small m is that mass that we want to throw with a certain speed. Obviously, we need to understand what change in gravitational potential energy has taken place. If initially it has this gravitational potential energy and at infinity its gravitational potential energy is 0, what is the change in gravitational potential energy? Change in gravitational potential energy is equal to 0 minus g m over R. If I simplify it, this minus sign will change to a positive number, gmm over R. So gravitational potential energy is gmm over R. If this is the increase in gravitational potential energy, that must correspond to a decrease in kinetic energy. If I throw an object with a certain kinetic energy here, which is 1 or 2 mv square, that is the initial kinetic energy here. If this is the enough kinetic energy to help this object reach infinity, that means the total change in kinetic energy is equal to half mv square minus 0, which is half mv square. That means the increase in potential energy must correspond to the decrease in kinetic energy. You can take it as 0 minus 1 over 2 m square. That will make it negative sign, but no need to make it negative. We just have to understand that increase in kinetic energy or gain in potential energy is equal to loss in kinetic energy. So I can equate these two. When I equate these two, I get a formula which can be understood in terms of these quantities. This will be cancelled. So 2gm over r under root. This is the value of V, which must be with which it must be thrown upwards, and this is its minimum value in terms of G, mass of that planet and radius of the planet, and this is easily calculable if we know all these values. If I know the value of G, which is given in the data booklet, if I know the mass of the earth, which is often given in the questions, and I know the radius of the earth, which is mostly known if you want to calculate the escape speed, using these values, it comes out to be approximately 8 kilometer per second, probably its value that you will be able to calculate. That means if you throw an object, a stone or a ball or a rocket or anything with roughly 8 kilometer per second, this object will not be able to come back to the surface of the earth. So this is the idea of the escape speed. Last thing that we can add to our discussion, that is geostationary satellites. Part of this is already done. There are many aspects of satellite motion we have already covered, so there isn't much left in terms of geostationary satellites, but there are a few points that remain to be discussed, and let's discuss them and complete our discussion of gravitation. Geostationary satellites, there are three conditions in order to qualify to become a geostationary satellites. Geostationary satellites are those satellites which appear to be stationary at their position above a certain geographical location. They do not appear to be moving at all. They remain permanently there, although they move, but exactly in what manner they move, so they do not appear to be moving. That is something we'll see now. So there are three conditions that are necessary to be fulfilled if a satellite is to be a geostationary satellite. Number one is if this is the planet Earth and this is its equator, a geostationary satellite moves in the orbit which must be in the equatorial plane. That means the plane of the orbit and the plane of the equator, they must pass through each other. This is one of the essential conditions for geostationary satellites. The orbit of a geostationary satellite geostationary satellite must be in the equatorial plane. Equatorial plane. Number 2 is the object must be moving in the same direction in which the earth is spinning. That means if the earth is spinning clockwise, if seen from below it is clockwise, then the planet, then the satellite must also be moving clockwise if seen from below. And if seen from above, obviously it will be anti-clockwise. So it will be either both of them moving anti-clockwise or moving clockwise seen from below or from above. So the motion of the satellite must be in the same direction in which the earth rotates. In which the earth rotates. So if it is rotation is like this, this must also be in this direction. And if the rotation is clockwise, if seen from above, the object must also be rotating in the clockwise sense in the orbit. Number 3, which is the most obvious requirement, that is the time that it should take to complete one orbital motion, to complete one round trip, must be same as the time taken to complete one rotation by the earth. So this is synchronization. The two must be synchronized in time. The time taken by the satellite to complete one round trip, must be 24 hours. So if Earth is completing one rotation in 24 hours, this satellite will be geostationary if it takes exactly 24 hours to complete one round trip. So these are 3 conditions for geostationary satellites. They often ask this question in the exam: what are the conditions so that a satellite is termed as geostationary? In order to calculate the height where a geostationary satellite may be launched, because that is always a fixed height, it cannot be more, it cannot be less. Let's quickly derive that expression as well, and that will complete our discussion for today. How to calculate the radius, calculating the radius of a geostationary orbit, which means this distance is to be calculated. And for this I go back to our initial equation that we used to derive various expressions, that was GMM over R square is equal to M R omega square. And if I quickly simplify it, this will get cancelled. Gm will be R cube, and this is omega square. And if I R cube, this is 4 pi square over T square. And this is Gm. This is the expression that we use to calculate the radius of the geostationary orbit, because we know that T is 24 hours expressed in seconds. So we know it. We know the value of G. We know the value of mass of the Earth. So using these values, we can calculate the value of the radius of the orbit, which will be of the order of 10 raised to the power 7 meter. So with this, we complete our discussion of gravitation. There are many questions for practice that remain. In the coming lectures, we'll continue discussing a few questions related to various topics. So you understand every concept carefully. I'll share with you some worksheets. The worksheets that I have already shared with you are not being done, and I have not received their solved versions. So work on them, ask questions. You can share your questions in the group as well. So we learn things, everyone knows what to discuss now. Thank you.